Thank you.
Yeah, and I changed the title from the one in the schedule. So let me start with a brief overview. So flavor mixing in neutron star mergers and core collapse supernovae is estimated to have significant effects on nuclear synthesis, on explosion dynamics. But as we've already heard, the quantum kinetic equation is very difficult to solve, maybe even computationally intractable in these settings. Um, and that's because oscillations occur on small scales. We just can't numerically resolve them throughout one of these environments. So this talk will present this transfer theory I've been developing to try to solve this problem. First, though, I want to talk about quantum kinetics itself and about whether this is in fact the right starting point. And the context here is that some studies have questioned the accuracy of quantum kinetics. They've taken this approach of comparing many body and mean field calculations that are based on this Hamiltonian. So in this kind of analysis, this term from neutrino-neutrino forward scattering is like a pairing interaction capable of entangling neutrinos. Um, and what this literature finds in their calculations is that neutrinos do become highly entangled. So if that is the case in reality, there may need to be a sea change in how we think about supernova and merger neutrinos. Um, but one crucial issue here is that this Hamiltonian is of questionable validity, and that's because um, it comes from requantizing the forward scattering Hamiltonian, which itself, the forward scattering Hamiltonian itself, comes from a kinetic treatment of neutrino propagation. And so the way it works is, you start from the mean field or the kinetic Hamiltonian, I'm using those terms interchangeably, and then you promote flavor states to quantum operators. So these would be like flavor polarization vectors, and then you add hats to turn them into quantum operators. But requantizing kinetics in this manner doesn't get you back to the original quantum many-body problem. And in fact, it fundamentally alters the physics. Um, so for example, like if you write this in the position basis instead of the momentum basis, you'll see that these neutrino interactions are infinite range when they should be zero range essentially. And so people have others have now followed up on this idea. Triliano, Sen, and Yamauchi recently performed calculations using the full correct many-body Hamiltonian. Um, and they do observe fundamentally different dynamics in their calculations, as opposed to what you see using the requantized Hamiltonian. So I've underlined the significant parts. They see thermalization of flavor and momentum on comparable timescales, um, which contradicts this widely accepted notion that flavor evolves on a time scale proportional to 1 over g Fermi, whereas momentum evolves on a time scale proportional to 1 over g Fermi squared, a much longer time scale. Um, and this is getting at, I think, an equally fundamental limitation, which is that these many-body calculations, these types, even if they use the correct Hamiltonian, are still not models where we would actually expect kinetics to apply. Um, so at present, there's no evidence that quantum kinetics is inadequate as a treatment of neutrino transport. Um, to go further with this, my collaborators and I came up with a different kind of many-body model that we think probably shows how kinetic behavior does, in fact, emerge. So we call this the once-in-a-lifetime encounter oil model. And the feature that this model has that past neutrino many-body models don't is that any two neutrinos only interact once and for a brief period of time. Um, and that interaction time we control using this parameter gamma. And so what this figure is showing is that as we decrease gamma, we're decreasing the duration of an interaction. And we see the emergence of coherent flavor oscillations. And you can tell from the flattening of this curve that you're moving into this coherent limit. So going forward in this talk, we'll just take it for granted that, that quantum kinetics is the right starting point. Um, but even with that established, there's an open question as to what the right paradigm is, if you will, for trying to solve this problem of oscillations in supernovae and mergers. Um, so let me go through the three paradigms that I think are currently on offer. So the first and oldest is direct numerical simulation of quantum kinetics. Um, I think nowadays this doesn't seem to be a very promising approach because you can only solve the QKEs um, in models that are too simple to be reliable stand-ins for actual astrophysical settings. Um, and so starting, like 3 or 4 years ago, there's attention um, shifted strongly to a different paradigm. I'm calling it asymptotic state subgrid modeling. The premise here is that fast flavor instabilities lead to quasi-steady asymptotic states. So this has been observed many times in oscillation calculations. Um, and so, the thinking goes, you can incorporate oscillations into a simulation in two steps. So first you step forward with your simulation without oscillations. And then in the second step, you search for regions that now have flavor instabilities, um, and you set the flavor distributions in those regions to these like post-instability asymptotic states, the ones that correspond to the unstable conditions. So there's an assumption here that because fast instabilities very quickly lead to these asymptotic states, you can like jump right over the transient dynamics and go straight to the asymptotic state. And then I've been advancing a third paradigm, which I've called misodynamics. So this is after the Latin word for mixing. I mean, the central idea is pretty simple. Um, you assume that neutrinos are in or near local mixing equilibrium. And what it means for neutrinos to be in mixing equilibrium is that this commutator vanishes. Um, so there's a close analogy between misodynamics and hydrodynamics, which is the paradigm for particle transport near local collisional equilibrium. Um, and if a system is in collisional equilibrium, then this collision term will vanish. So you can see at this level the parallel between the two. In a sense, misodynamics is actually the transfer theory that lies in between kinetics and hydrodynamics. So each scale separation is a good opportunity to perform a coarse graining and formulate a new transfer theory. Kinetics is a coarse graining of the exact quantum many-body dynamics. I was arguing in the first part of this talk that this is an appropriate coarse graining here. In some systems, hydrodynamics is an appropriate further coarse graining, but it's not appropriate for our purposes here because in the regions where neutrinos are oscillating, collisions are too weak to bring them into local collisional equilibrium. And that goes back to this fact that oscillation rates are proportional to 1 power of G Fermi, whereas collisional rates are proportional to 2. So we have this scale separation. And so misodynamics proposes to coarse grain over the oscillation scale using this assumption that oscillations are in local equilibrium in much the same way that hydrodynamics proposes to coarse grain over the collisional scale by assuming that collisions are in local equilibrium. At the same time that I've been advancing this misodynamic or local equilibrium paradigm, I've been making this argument that the asymptotic state paradigm really isn't self-consistent. And I think the easiest way to see this um, is to note that if fast instabilities are instantaneous, they occur, infinitely quickly, um, then angular crossings, which are the precondition for fast instabilities, can't form in the first place, because as soon as an angular crossing is beginning to form, it'll be immediately wiped out by a fast instability. In fact, the assumption of rapid or instantaneous relaxation, flavor relaxation to local mixing equilibrium, or an asymptotic state, whatever you want to call it, is the first of three ways I'll show in this talk to arrive at the misodynamic equation. Um, so in other words, the assumption that's been used to justify asymptotic state models, if you follow its implications through, it actually doesn't lead to asymptotic states, it leads to misodynamics. So to see this, let's make a relaxation time or BGK type approximation for the Hamiltonian. We're approximating the effect of oscillations as quickly bringing you to some equilibrium or asymptotic state. So we're introducing a relaxation parameter that we take to infinity. Again, we want instantaneous relaxation. And I'm already calling this rho EQ, but really this is just, some state that relaxation locally brings you to. So asymptotic state models would say that, rho EQ should be one of these post-instability asymptotic states, right? But for what we're doing on this slide, we don't want to assume what rho EQ is or how to calculate it, because we want that to be self-consistently determined by this approximation that we're making, this approximation of instantaneous relaxation. And so in this limit that gamma goes to infinity, rho clings perfectly to rho EQ. You'll only have very small deviations. So it's set rho to rho EQ. That immediately gets you to the misodynamic equation, which is this supplemented by an additional self-consistency condition. This comes from requiring consistency with the underlying approximation, right? So we say rho is equal to rho EQ, the whole thing should vanish. So we want the commutator to vanish at equilibrium. Um, and so we see from this that that this symbol rho EQ really does mean local mixing equilibrium. This was the definition we gave a few slides back, rather than an asymptotic state. And so from these equations, we can see I think the two essential qualities of misodynamics. So one is is that mixing equilibrium is driven by the astrophysics, which I also take to include advection and collision. So basically, what a simulation is already doing, everything but oscillations. And the second feature, again, is that the equilibrium is self-consistently determined. Part of that involves the fact that H depends on rho. So that's what this symbol EQ means on H and C. This is just, so H depends on rho through neutrino-neutrino forward scattering. So it's a function of, in this case, rho EQ. That's what the symbol means. Just to clarify what C means here, those would be like your same Boltzmann collision integrals, but your distribution functions are now the density matrices evaluated at mixing equilibrium. That's the meaning of that. So, I mean, oscillations drop out entirely, right? So this can kind of be a puzzling equation, but the key is that you have to evolve it while satisfying this condition at all times, the local equilibrium condition. Okay, so now I'm going to show a different way to arrive at the same point. So forget about relaxation to some equilibrium state, right? So here, instead, what we'll do is we'll consider expressing rho as so it's just the flavor anywhere in a supernova, let's say. You express it as a fine-grained deviation from a local average, the coarse-grained average. And this coarse graining here is in time and space. So you can imagine that you've divided up the supernova into cells in time and space. Sorry, let me just explain these assumptions before I show that. So we're assuming two things. One, that these coarse-grained averages change slowly. That means now we're assuming that that averages change on an astrophysical scale rather than the much smaller oscillation scale. And we're furthermore supposing that these fluctuations from the averages are uncorrelated. So we're treating the fine-grained oscillation dynamics as just being like random fluctuations. And then now, imagine coarse graining the quantum kinetic equation. The key thing is what happens to the oscillation term, that commutator. So we take the coarse grain value of the commutator and it becomes the commutator of coarse grain values plus this correlation term, which vanishes by assumption. But this remaining term also has to vanish because if it didn't, then coarse grain averages would vary on the oscillation scale. This term would drive evolution on that small scale. So to be consistent with this idea of slowly changing averages, in fact, we need the entire oscillation term to go to 0. And so in this case, now we're just going to define this EQ symbol to mean the coarse-grained average. But then we see that, well, this equilibrium label is appropriate because we get back to the misodynamic equation and the coarse-grained rho does satisfy the condition of local mixing equilibrium. So these are related viewpoints, but they're different, and different motivations for misodynamics. And again, they're based respectively on rapid relaxation and uncorrelated fluctuations, this idea that we don't really know anything about the fine-grained dynamics. Why would quantum kinetics have these features? So later in this talk, we'll explore flavor ergodicity and neutrino quantum thermodynamics as possible more foundational explanations. At this point, though, I want to emphasize the fact that we haven't used a hypothesis that flavor evolution is ergodic or thermodynamic. And I'm emphasizing this because in the paper where I introduced misodynamics, it was in this context where I was first formulating this thermodynamic theory of neutrino oscillations. And so I think it gives the impression that you have to accept like this oscillation entropy I defined and a bunch of other stuff in order to get to misodynamics. But as we've just seen, that's not the case. And so the thermodynamic treatment will be the third pathway to misodynamics. Right. So the equilibrium there would be coarse graining over the entire box that you're solving, right? So this is like a periodic box oscillation calculation. Yeah, and so it would, essentially the mixing equilibrium would correspond to the asymptotic state in that situation. And so there's agreement that like these coarse grained values do reach asymptotic values, although you do have ongoing small fluctuations, right? But they're not huge. They're not huge. And the significant thing about misodynamics, though, is that it's telling you how to move between equilibria, right? So there is a sense in which it sort of, agrees that asymptotic states are, right? It's not like inconsistent with asymptotic states, but it tells you how to move from one of these boxes to the next one, both in time and space. It connects equilibria. Yeah. Why there's what? Oh, that is because at the very least, we want to consider the fact that the Hamiltonian depends on rho, so you would have a delta H from delta rho. Yeah, but you could also imagine, like you could imagine applying misodynamics to the MSW effect, and then um, delta H in that case would be would refer to the fact that the matter density changes within a coarse-grained box. That's by assumption. Yeah, yeah.
H delta rho vanishes by assumption, the commutator.
Yeah, yeah, that
Why do you assume that?
right. So this really is like the content of the approximation. It's that we're going to say so for simplicity, let's suppose that delta H just does come from delta rho, right? So really these are like correlations delta rho delta rho. We're just seeing what is implied if you make this approximation that fine grained details in flavor are random, just random fluctuations around averages. Yeah. And again, why would you make that? I mean, so I have this idea that maybe it's because there is a sense in which flavor behaves thermodynamically, um, which in turn could be traced back to an idea of flavor ergodicity. So I'll get into some proposals as to why that might be a good approximation, but those are even more speculative, right? So that is so in this case, we're getting that as an output, right? Yeah. So we're saying that if you take this viewpoint that fine-grained details are fluctuations, then you are forced into this situation where rho is always diagonalized in the energy basis. H and delta rho. So like, um, well, because we are so like we're taking um, the coarse grained value of that term as well. So it's like, you would have the coarse grained value of the commutator of average H, now average delta rho is what it becomes. I don't know if I said that correctly. You would end up having, so H just kind of like passes out of the coarse grain average because you're already considering the average in that term. So the averaging is just on delta rho, but we're saying that, that average of delta rho is equal to zero. With with delta H and rho. Yes, right. And so like part of that will be a term that again yeah, there probably is like something more to that assumption, like how the Hamiltonian varies. I mean, because you're going to have this term that's like delta H delta rho. It's like the derivative of H, the variation of H delta rho. And so yeah, there's something. I think you're right. I think there's something more to that. Yeah. 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 Right. Yeah. Yeah. Exactly. I mean, so like the Hamiltonian is linear in rho. So if you assume, so I mean, you're going to have a potential that's basically like, you know, G Fermi times rho, and so it just becomes delta rho and does actually vanish. But in general, you could imagine that there's more you need to assume. Yeah, I mean, it's a combination of both, right? I think there's like something physically appealing about this. Um, you can kind of think of it from, again, from different perspectives, but it's like, well, what if we just assume we don't have any information about what happens at small scales, assume that they're just random fluctuations for that reason, kind of, epistemological argument. Again, that's like pushing us in the direction of thermodynamic reasoning. Yeah, I mean, I can't say that any of these assumptions are correct, but the reason I'm giving like different pathways to this is because they all lead to the same end result, but one may appeal to you more than another. So before we get to the thermodynamics stuff, just want to make one more general point about misodynamics, which is what this theory is doing from one perspective is it's generalizing adiabatic quantum evolution. That's kind of at the heart of this. And so I'm calling this MSW adiabaticity just to put everything in a neutrino context, but this is just the classic textbook concept of adiabaticity, right? A quantum state tracking an energy eigenstate. So collective oscillations have actually already prompted a generalization of this concept. I call it Rafold-Smirnov adiabaticity, a generalization to apply to nonlinear quantum mechanics as you encounter in mean field and quantum kinetic theories. So again, H depends on rho, so we have nonlinear quantum mechanics in this case. And then misodynamic adiabaticity is a further generalization that additionally includes inhomogeneity, advection, and collisions. So like what I would say is that it's including grid level physics in the context of a simulation. Oscillations are subgrid, the nonlinearity is subgrid, that's part of neutrino-neutrino forward scattering. And then misodynamics is telling you how to move adiabatically from one of these coarse-grained cells to the next one, and how to do that adiabatically. Yeah. Yeah. Yeah, so actually what I've been presenting is the adiabatic theory, and I'm still working on developing these non-adiabatic corrections, which may or may not be important. I'll say more about that in a second. But this equation, strictly speaking, is the adiabatic limit of misodynamics. The reason we got to adiabaticity in both of these treatments is because we've assumed, essentially because deviations from mixing equilibrium are taken to be completely unimportant. So you're in this limit where you are always perfectly in equilibrium. If you were to consider the corrections that come from deviations from mixing equilibrium, you would be led to non-adiabatic terms that are analogous to a viscosity in hydrodynamics. So in a sense, this is analogous to like the Euler equations. Just to repeat it, so this actually is the limit of adiabaticity, okay? And so what this generalization, again, going back to the adiabatic concept, means in particular is that now we can have adiabatic incoherent evolution. And so like in MSW and Rafold-Smirnov adiabaticity, the slowly changing control parameters are parameters in the Hamiltonian. In misodynamic adiabaticity, we can talk about adiabatic processes where the control parameters include these flavor polarization magnitudes, which are constant under coherent or Hamiltonian evolution. But now we're saying you could have incoherent physics like collisions changing those terms gradually, and that is driving an adiabatic process in this sense that oscillations are in equilibrium while those incoherent processes are occurring. For example, so I mentioned the oil model. So this is a toy model, but in addition to having value for these many-body issues, it's also interesting because it shows this complex flavor relaxation. So like you can just see it in this panel. You have non-exponential flavor decoherence, right? This is very puzzling to us when we saw it, and I won't say a whole lot here. Just this kind of flavor evolution hadn't been observed as far as I'm aware or anticipated. But misodynamics explains it. So misodynamics is, so for the dashed curve, we've solved the misodynamic equation and we're comparing to the quantum kinetic solution. Yeah, so it's like so we have two groups of particles and we keep it goes back to this oil model. So I say we're solving quantum kinetics, we're actually solving this many body model that reproduces kinetics. And it's like the two particles interact briefly, develop some correlation, and then we decorrelate them. So it's like we trace out the other particle and go back to this single particle description, and we keep doing that. We have a bunch of different neutrinos in two different energy groups in this calculation. And then the third is the yeah. So that is PZ, which is you know, essentially like the flavor asymmetry in the two groups, like the amount of nu E minus nu mu. Yes, we get flavor equilibration eventually, and you know, it's kind of like an equipartition up to this conserved lepton number quantity. What's interesting about it is that before you get there, it's like you have this long period where it seems like no relaxation of flavor is occurring, again, in the diagonal elements in the flavor basis. And then all of a sudden you like go through this, we're contemplating the idea that this is related to a phase transition. Again, there's potentially like a thermodynamic interpretation here. Mm. I would ask you to say more, but I'm short on time. It's like around, it's like 60 in one group and 40 in the other. And so, I mean, so really what we're doing is like any two neutrinos in a certain sense can see each other again, but because we decorrelate them, it's like they're seeing each other afresh. Yeah, it's like a molecular chaos assumption. So this, again, this is a many-body model that was meant to kind of have built in the assumptions that we use in deriving quantum kinetics. And then we just realize that it has this interesting and kind of hard to explain flavor relaxation. And then it turns out that misodynamics accounts for this. So this is an example of this like adiabatic incoherent evolution. Uh, it yeah, okay. Okay, so I think I think this is like per particle in the group, and they have different numbers. So yeah, so the conserved quantity is like a weighted value times the value in the plot. Yeah, yeah. Okay, so let me summarize the current status of misodynamics. So again, the adiabatic theory is what I've been presenting. That's largely complete. I mean, I think pretty much ready to be implemented into simulations, with a caveat that I'll get to in a second. The non-adiabatic theory, which it takes into account finite and correlated deviations from mixing equilibrium. Again, these are like viscosities, you could say. Still working on that. There are definitely some oscillation models where you need the non-adiabatic theory to explain the results. And so misodynamics just doesn't yet make predictions in those cases. On the other hand, it's unclear whether we need the non-adiabatic theory for astrophysical purposes. It's conceivable, I think, that the neutrino flavor field is constantly adjusting itself to maintain adiabaticity, even to the point of preempting flavor instability. Like the flavor field kind of may be approaching conditions that would be unstable if it were not for this kind of adiabatic adjustment, rearranging itself in flavor space. So I call this the adiabatic hypothesis. I'm definitely not saying I'm not predicting this is true. I really don't know, but I think it's a possibility that needs to be considered. And if you buy it, then you could just go and implement misodynamics into a simulation now. Well, yeah, this is like 2/3 of my talk, but I see we're Yeah, out of time. Okay. Let me think about what to do here. I'm going to, can I take maybe 3 more minutes to just say what I would have said? Um, so, so there were 3 more sections. I'll be very brief about this. So flavor ergodicity is this proposal that, so you apply the ergodic hypothesis to motion and flavor space. It's the idea that neutrinos uniformly explore all accessible parts of flavor space. Okay, accessible is the key word here, but I won't go into detail on this. And then this statistical way of thinking about neutrino oscillations can then be used to turn neutrino quantum kinetics into neutrino quantum thermodynamics. And so if you use so ergodicity allows you to replace, long time averages by ensemble expectation values. Basically, we just apply that idea here. I'm again using this term rho EQ, but what I mean by that is an ensemble expectation value. The ensemble is the ergodic subspace. It's the motion explored in flavor space. You can define an entropy that you maximize, subject to the constraints that define your ergodic subspace. So basically, it's like the idea here is that you would fix whatever quantities are actually conserved microscopically by oscillations. There's stuff you can do with this. I'm still trying to figure out what it's useful for, like how to use it. But just to give you, just as an illustration, if you suppose that the total energy is fixed and also the neutrino number at each momentum, and you vary this entropy, you get an equilibrium distribution that's generalizing the Fermi-Dirac distribution to include quantum coherence. But here, beta is not it's not associated with an external environment. Again, these are like collisionless, isolated neutrinos. So that is a heat bath that effectively arises from the small scales you're coarse graining out. It's a Lagrange multiplier, ultimately. So that would be by self-consistency with keeping the total energy constant. So like you would have an equation that's like total energy equals some integral, an energy-weighted integral over the distribution, and then you plug this distribution, and you have to fit beta to that. Yeah. Okay. Anyway, a lot more to say here, but I'm going to skip ahead to this last thing and just highlight collisional flavor instabilities in the context of this storyline. So these are instabilities that are caused by the asymmetry between neutrino and antineutrino interaction rates. It's a fairly new phenomenon, but we actually already have evidence from linear stability analysis that these are prevalent in supernovae mergers. But what makes them stand out is that their growth rates are usually like a kilometer, give or take an order of magnitude. So they're instabilities that really are like at the grid level, and in that sense put pressure on subgrid models. I think they're compatible with misodynamics, but I'm just pointing this out as something that I believe as a community we're like really just starting to think about. I mean, the fact that you can't think of collisional instabilities as growing on a static and homogeneous background makes it very difficult to even estimate what their probable effects are. So we know a lot less about them right now than we do about fast instabilities. Okay, so I'll end there. These are the 5 sections. Thank you.
Okay, are there further questions or comments? Yes.
Thank you, Luke. I have 2 related questions. So the one is about this recent work that you flashed about Ciriliano and company, where they claim they reached thermalization. And I understand that this is reached in a system with 10 particles. So is the thermalization, the achievement of thermalization is affected by the number of particles, or is this independent?
Well, so they don't claim to see a pattern. And I mean, yeah, I've been thinking about this lately, like maybe it could arise, but I don't know that we expect, as you take n to infinity, to see this like G Fermi squared separation forming. And in a way that kind of contradicts how, like, that would contradict the way people have thought about these mean field limits, whereas you take n to infinity, you just get the G Fermi term. And G Fermi squared is negligible.
Yeah.
If you try to map them up to each other.
And the related question is about these results that you were showing where you go to equilibration between neutrinos and antineutrinos, where it seems you have 100 particles.
Yeah.
So is this the same conclusion that they reached, or is this like a system which is acting differently because of the assumptions that they are making?
It's acting differently because of our assumptions, right? And so our motivation was, even in their model, it's like, I think from my standpoint, what their model brings out is that all of these past many-body models are not the kinds where kinetics emerges, so we just wanted to say, like, well, if you kind of make these assumptions, then you can actually have a different sort of many-body model where kinetics doesn't emerge.
I see. Thank you.
So how do you put these boxes together? What's in your mind? I mean, do you imagine like a one-dimensional thing that you reach equilibrium in one box, then they all move to the new box or to the next box, where the external conditions are different? Or do you have in mind like a more two-dimensional array of boxes?
Yeah, I mean, I'm thinking about it in 3 dimensions, in fact. I mean, I don't know if I'm like imagining that, but that's the idea that, you know, that is what the misodynamic equation is meant to do. I mean, again, you can kind of think of this adiabatic limit of misodynamics as a way to impose quantum adiabaticity in situations where you have like stuff moving in 3 dimensions, right? And also incoherent processes like collisions. As opposed to having like a control parameter that's simply a function of time. Now you have a whole set of control parameters that are functions of time and space. So this is like adiabaticity in that context.
What about the toy model that, I mean, not the toy model, but the example that you showed?
Yeah.
What kind of evolution was that a one-dimensional evolution?
That is, so the equilibrium is a function of, in that case, of the, so there's this conserved quantity plus the magnitudes of the polarization vectors. So collisions, so this is why that, even though it's a very simple model, you get like this complex relaxation. It's that the effect of the collisions are coming from neutral current neutrino-neutrino interactions. And so the flavor decoherence depends on the states of the neutrinos. It depends on the current flavor states. So there's this kind of feedback from the current flavor state into the nature of decoherence. And misodynamics is kind of naturally taking that into account. It's making sure that the way the polarization vector magnitudes decay is consistent with always having oscillations in equilibrium. Because because of this feedback, there are like many ways that you could decay. You don't simply have like an exponential decay that's proportional to a damping rate or something.
Okay. Gunther. Gunther. Okay.
Maybe I misunderstood. In the beginning, you said you know, when you have correlations between different momentum modes, that comes from re-quantizing the thing. But this I didn't understand, because if you start with second quantization, you always have creators and annihilators, and in general, of course, they are correlated. And then you make a mean field approximation, and then you get the kinetic equations. So what do you mean by re-quantizing?
Right. So, what I mean is, and I'm going to kind of reiterate what you just said. Like, really, the way we get what people often refer to as the mean field Hamiltonian is through this kinetic analysis where we expand in G Fermi, right? And there's this idea that you can kind of, I mean, it's a scattering-based approach, so you can imagine doing perturbation theory in G Fermi or in short interaction times to get the evolution during one interaction, and then you assume that particles decorrelate so that the next time there's an interaction, it looks the same. And that's how you get like a row dot that just has like a G-Fermi gene. Yes, exactly. And so the point I'm making is that that molecular chaos assumption is actually key for why you get forward scattering as this apparently dominant term, as this sole G-Fermi term. But then if you drop all the higher terms and you requantize the G-Fermi term. So again, so now you have like, rows, density matrices that you now turn into quantum operators. So you go back to A dagger A's. That doesn't get you back to the original physics.
Okay.
Yeah.
No, Sergey, okay, please. Okay. No, okay.
We have been discussing this with Lucas since I came here, and I disagree with him on this. So the cutting off of the second term effects, the collisional effect, momentum transfer effects, is about perturbation. So my standpoint is that there are two separate approximations. One is treating the self-interacting. So they have a self-interacting field. You can treat that within the first-order perturbation theory. And that throws away GF squared terms and the collisional terms. So what remains is only the forward scattering terms. Then you make a second assumption of saying that your test particle and the other neutrinos are unentangled. So what you call requantization is not making that second assumption, just the first assumption. Just treat it non-perturbatively, but treat it perturbatively, but keep possible entanglements. Don't cut the Hilbert space. So this is something that you say that it doesn't take you back to the original quantum many-body state. I agree, but it gives you a model in which entanglements are allowed, but you are still in first-order perturbation theory. That, I agree. But it's not a second quantization. It's not a requantization. It doesn't take you back to the original theory, but it takes you one step back, not two steps back, obviously.
So maybe last comment, Sergey. Yes, please.
It's just a comment. I'm very interested in the adiabaticity and non-adiabaticity condition. And then until I see it written, I cannot get it, really. Yeah. So I want some kind of analytic expression in order to understand what you mean by Mishi dynamics, adiabaticity or non-adiabaticity.
And just to clarify, so what would you want to see written, like an adiabaticity criterion?
So there should be some analytic stuff that describes this situation.
Yeah. Right. Yeah, so like the non-adiabatic terms in the misdynamic equation, I just don't know what they look like yet, right? As far as an adiabatic parameter, something that tells you, like estimates the size of these effects. So that, basically will just be kind of like a generalization of, at least like this is the lowest order in some sense, a generalization of how we think about the adiabaticity parameter for MSW, but it's like, how fast any Hamiltonian in the system, so you have like H sub Q for different momenta, how fast any of those Hamiltonians is changing relative to its magnitude.
In the MSW effect, what matters are the oscillation parameters, not only, it's a relative thing. It is the change of density relative to certain oscillation parameters.
Yeah, so what I was saying is it's a change of the Hamiltonian relative to the magnitude of the Hamiltonian. The magnitude of the Hamiltonian is where the oscillation parameters are through the vacuum part of the mixing. Through the vacuum part of the Hamiltonian, I should say.
And in the Hamiltonian, what changes? The density or what?
It depends on the process you're considering.
No, but in your case, in the case you are considering, what is changing fast or slow?
So in the general case, like if we're thinking about this in a supernova, it'll be like the electron density changes, right? So you're moving forward in a simulation, and you want to make sure that everywhere you've moved adiabatically. That means, you know, particles, if they stay in the same cell, they've moved adiabatically. If they transition to another cell, they've done that adiabatically. And so the control parameters, the control parameters are things like the electron density in any given cell, the neutrino densities in any given cell, these flavor polarization magnitudes, and other things of that nature. Anything that enters into the Hamiltonian. That's the short answer. Anything that enters into the oscillation Hamiltonian, because that's what defines mixing equilibrium, and mixing equilibrium is the, you know, the condition that misodynamics has to satisfy.
Okay, maybe you can continue during the break. Yeah. Okay, let us thank the speaker again.